Once upon, some 2,800 years before the Common Era, around the city of Lagash, a middle-aged man received a delegation from the Sumerian king. They brought amounts of a rock and a royal edict. Enki Idinam was thinking. While his helper prepared the fire, he was worried about the experiment he was about to carry out. He wanted to please his king, presenting him with the special dagger he was ordered to forge. His status as the owner of sacred secrets, the one that kings respected, people revered, and some even feared the status he rightfully deserved, was about to be challenged. An envoy of the Sumerian king brought a large amount of a mineral that merchants had specially obtained from the Iranian plateau, where a man called Kaveh was said to be able to produce a better type of copper, more suited for tools than the one used for ornaments. Welcome to the podcast Chemistry Forging Civilizations, where we unfold the molecular hidden secrets that made our civilization. Chemistry, the science that studies changes in matter, changed humankind. When man started to walk the earth, he found stone and flint, he found wood and bone, he found obsidian, and he made tools of them. And so it was for hundreds of thousands of years, until he found copper. This is a chemical and sociological story of the tools that replaced stone and obsidian. Before the Iron Age, before even the Bronze Age, there was copper. It was the first metal that humans shaped, and it shaped us in return, chemically proficient, technologically, and socially. But to understand copper's impact, we must start not in the forge, but in the earth. A view of the distant past. The earliest evidence of copper use dates back over 10,000 years in the Middle East and Anatolia. But it wasn't smelted. These were native copper nuggets, hammered cold into tools and ornaments. Smelting, the process of heating a metal containing rock, a mineral, to isolate the metal, copper in the Chalcolithic era, is more recent. By around 5000 BCE, in places like Mesopotamia, Anatolia, and the Iranian plateau, humans began to smelt copper from ore. Egypt started somewhat later, and China started well into the Bronze Age. This was more than just a technological milestone, it was an alchemical transformation. For the first time, humanity could pull metal from stone. In antiquity, this felt like magic and gave the smelters prestige and almost priestly status. With this, copper became the foundation of the first metal-based economies. Why copper? Unlike stone, copper tools could be sharpened, reshaped, melted, and recast. It wasn't just useful, it was reusable. This recyclability made copper an early form of stored value, and it transformed social structures. Smelting copper required specialists. Smelting involves identifying and collecting the right ore, crushing and roasting the ore to drive off CO2 and water. Building and operating furnaces that reach 1080 degrees Celsius. Maintaining or reducing atmosphere, a low oxygen environment, to convert copper oxide into metallic copper. This needed skilled control of charcoal to ore ratios, mastery of airflow via bellows or blowpipes, timing and observation of color and texture cues in the furnace. Not just anyone could extract, refine, and cast it. This created the first craft guilds, the first technological elites. Metallurgy became a form of power, both in knowledge and in control of resources. We see this clearly in early urban centers like Ur and Çatalhöyük, where copper artifacts became status symbols. Weapons, cult objects and tools, jewelry. Copper was a marker of prestige. And with metallurgy came trade. Regions with copper deposits like the Timna Valley in Israel or Cyprus in the Mediterranean became central to early trade networks. Metallurgy tied societies together in webs of exchange, diplomacy, and sometimes war, extracting copper in ancient times. Copper exists in natural compounds on two states, monovalent and bivalent copper Cu plus and Cu plus 2. It is a transition metal whose electronegativity is relatively high, being 1.90 in the Pauling scale. It is then readily oxidized, losing 1 or 2 electrons to oxygen to produce cuprous oxide, Cu2O, which is naturally disproportionated, meaning undergoing self-reduction and self-oxidation, in an acid environment as follows. 1 molecule of cuprous oxide in an acid media will produce 1 of a copper-2 solution and 1 of metallic copper. In nature, this process could occur in the presence of carbonate and water or a sulfuric or even carbonate environment. But in the ancient world, this property also made copper reactive with air, water, and carbon compounds, producing copper-containing minerals like this mixed malachite and azurite rock. Early copper ores were not metallic lumps waiting to be carved. They were minerals, cuprite, which is the oxide of monovalent copper, cuprous, with 2 copper atoms per 1 oxygen atom, malachite, which is a hydroxycarbonate of a copper bivalent, cuprisk, whose basic unit has 2 copper atoms, 1 carbonate CO, 3 anion, and 2 hydroxyl OH units. Azurite, which is a different hydroxycarbonate of bivalent copper, containing 3 cupric atoms per basic unit, 2 carbonate groups, and 2 hydroxyl groups. These minerals had to be chemically transformed. Smelting, the key breakthrough, involved heating copper ore with carbon, typically charcoal. This reduced the copper oxides and carbonates to pure metallic copper. The reaction for cuprite looked something like this. Each molecule of the cuprous oxide in the cuprite would react with 1 carbon when heat applied and be reduced to metallic copper, while carbon monoxide escapes. It required high temperatures, around 1100 degrees Celsius. Not an easy task. But once early humans figured out how to build furnaces hot enough, they cracked open the metallic age. The chemistry of copper smelting. Cuprite is a copper monovalent oxide. When reduced with carbon as charcoal, it produces copper metal and carbon monoxide. Or, if excess carbon is used, carbon dioxide is produced. Smelting malachite involves 2 steps: thermal decomposition followed by reduction. Step 1. Calcination, heating malachite in air, produces cupric oxide, carbon dioxide, and water. The black copper oxide is then reduced. Oxygen is lost, electrons are gained by copper, with charcoal. 2 moles of cupric oxide, CuO, plus 1 mole of carbon when heated, produce 2 moles of metallic copper and 1 of carbon dioxide, CO2, that is eliminated as a gas. And copper is obtained, ready to manipulate into tools and ornaments. This one from an experiment performed in 2023 in the Timna Valley, from copper to arsenic bronze. When our hero Enki Inami saw the grayish-black rocks with brown-black streaks, he recognized the rocks from similar ones he had seen in his youth in the Taurus Mountains. He prayed to the god Enki, whose name he carried, god of the earth, for success in the task he was about to take. He knew that if he was successful, he would have an accessible source of the material from which he would make tools fit for the king. Nowadays we call the mineral he was about to smelt tennantite. It contains arsenic and sulfur as well as copper. A molecular unit contains 12 atoms of copper, 4 of arsenic and 13 atoms of sulfur, Cu12As4S13. And it produces a copper alloy that's less porous than copper itself. As a consequence, it is less brittle and can be smelted into larger tools. Sumerian daggers have been found to be larger than daggers from other regions, measuring an average 15 centimeters longer and containing 2% to 5% of arsenic. How can we know the composition of those archaeological tools? The go-to method is X-ray fluorescence. Fluorescence is the emission of radiation following the excitation of the object by a strong energy source. In the case of XRF, the object is submitted to a strong X-ray source, which causes electrons in the inner layers of the electron shell of an atom to be kicked off. As a consequence, electrons from the high-energy outer layer of the atom rush to fill the vacant layer, which has lower energy. As a result, radiation is emitted in the form of X-ray fluorescence in a pattern that is characteristic of each element. This picture depicts the characteristic XRF spectrum of arsenic, with emissions at 10.5 and 11.7 kiloelectron volts. Back to the past, back to Enki Inami. He was warned that smelting the mineral in question produces vicious fumes that can cause irreparable injury and death. His helper prepared a pit that could be closed, if not sealed, in order to trap the fumes and produce a better copper. The smelting of tennantite starts by thermal decomposition of the ore. In the presence of charcoal and limited amount of oxygen, some arsenic is incorporated into the copper and does not escape as poisonous arsenic hexoxide, As2O3. Sulfur is retained as copper sulfide and solid sulfur, instead of the also poisonous sulfur dioxide SO2. When the further reduction of the copper sulfide proceeds with charcoal, carbon monoxide, which is also poisonous, is also produced. In summary, the final products are arsenic bronze, arsenic sulfide, CO, and solid sulfur. So, in order to conduct smelting, he situated himself and his helper with the wind on his back and lit the improvised furnace. From stone to copper, the Chalcolithic period set the stage for the first agriculture and organized societies. Whether there were axes, arrowheads, sickles, knitting tools, or daggers, agriculture and conflict on a large scale were starting to take shape. The birth of a new age, the Bronze Age. Copper limitations, like being easily oxidizable and somewhat brittle, pushed the search of improvements, of which arsenic copper was the first one, and set open the stage for experimentation and primitive metallurgy. The archaeological record shows that at the middle of the 4th century BCE, a new copper alloy starts to appear, spreading from Mesopotamia into Egypt and Europe. Bronze. This is an alloy of copper containing 5 to 15% tin. Thus, around 3500 BC, we signal the start of the period we now call the Bronze Age. It lasted for almost 2,000 years, till about 1200 to 1150 BCE. Why has bronze such importance that we distinguish the period of its prevalence use as a different archaeological and historical period? Arsenic bronze was probably discovered accidentally when casting tennantite for copper. The most abundant tin mineral is cassiterite, an oxide of tin SnO2. The second most abundant mineral is stannite Cu2FeSnS4. However, even if it contains copper, it is by far much less common than cassiterite, particularly outside Latin America. It is possible that cassiterite was intentionally tested when looking to improve on arsenic bronze. Tin bronze replaced arsenic bronze because it is easier to cast and control, allowed mass production of weapons and tools, can be handled in a more predictable way, less toxic, safer for larger scale production. It allowed to handle large molds for production of decorative art, weapons, wheels, and more consistent military equipment. Bronze melts at about 100 degrees lower than copper. Molten tin bronze flows more easily than either copper or arsenical bronze. This makes it ideal for filling molds completely, especially complex or thin-walled shapes like spearheads, blades, and decorative or symbolic items. While arsenic bronze could be brittle, tin bronze is tougher and more ductile. And while arsenic bronze strength was inconsistent, tin bronze is uniformly stronger. What makes bronze stronger than just copper? When molten tin is added to molten copper, a metal solution, a solid alloy, is formed when cooling. The tin atoms, larger than copper, dislocate the copper lattice and make it harder for the copper layer to slip and the tool to deform. However, if the amount of tin is larger, intermetallic compounds form where copper and tin actually bond chemically in a fixed stoichiometric ratio, like Cu6SN5. This would void the advantages of bronze, making it brittle. This made bronze the best available material for agricultural work and weapons. The use of bronze for plowing and harvesting brought an abundance of agricultural produce unprecedented in older times. With the increase in agricultural produce, a city or ruler's wealth increased. Commerce increases as well, with the need to obtain tin from nearby and sites as far away as the British Islands. So does the ruler's appetite for conquest increase. The Bronze Age see a surge of strong empires. Cities coalesced into kingdoms and kingdoms into empires and spheres of influence. Akkadians, Egyptians, Babylonians, Hittites, Elamites, Mitanni. The Bronze Age came to a rather abrupt end between the years 1200 to 1150 BC with the invasions of the Sea Peoples. Cities fell, empires crumbled, and the use of bronze was gradually substituted for iron. Iron, a stronger metal that melts at an even higher temperature than copper, but is extremely abundant and does not require the extensive commercial networks, which crumbled rather suddenly. What came later was an endless road of infinite possibilities, eventually leading to our own steel and special alloys civilization. Copper was relegated from its position of forger of civilization and remained in secondary role but always present until the Industrial Revolution. Scholars estimate that the Trojan War took place at the time of the collapse of the Bronze Age. Is it possible that the great fleet of the Achaeans, led by Agamemnon, was one of those sea peoples that hit the Egyptian and Hittite empires? What do you think? This is a recreation of the duel between Hector and Achilles that is sung by Homer in the Iliad. What do you think the real swords were made of? Bronze? Iron? Give us your opinion in the comments. The role of copper in the modern age, again forging civilization, but this time not alone, will be the subject of another video. If you enjoyed this one, give us a thumb up and subscribe, and you will get a notification each time we release another video. To see how the humble molecule of glucose rewrote the laws of the church, click right here for our episode on paper.